Okay, let's dive into this. You know, we use our computers every single day, but have you ever just stopped and wondered what is really going on deep down inside that processor? How do all our complex commands, our clicks, and our code actually turn into action? Well, today, we're going to peel back the layers and look at the secret, fundamental language of the CPU itself. See, it all really boils down to this one question. When you click a mouse, type on a keyboard, or run a big program, you're kicking off this incredible chain reaction. But what does that reaction look like at the absolute most atomic level of computing? Well, the answer lies in a set of commands called opcodes. So an opcode, which is short for operation code, is basically a verb for the processor. I want you to think of your CPU as a master craftsperson in a workshop. Opcodes are the simplest, most direct commands you can give it. Get, add, compare, move. They are the absolute bedrock. I mean, everything a computer does is built on these tiny instructions. So let's step inside this virtual workshop together. What's the very first thing any master craftsperson does? They organize their materials, right? Before you can build anything, you have to get the right pieces of wood and the right tools onto your workbench. In our CPU's workshop, there are really two main places to keep stuff. First, you've got this vast warehouse, which we call memory. It's huge, it can store almost everything you need, but, it's a bit of a walk to get things from there, so it's a little slow. And then you've got the workbench, sitting right in front of our craftsperson. These are the registers. They're much smaller, but they are super fast and easy to access. So job number one is always getting the right materials from that big warehouse onto the immediate workbench. And that's exactly where these first opcodes come in. The move command, that's like telling the craftsperson, go to the warehouse, make a copy of this piece of data, and put it on the workbench. XCHG is even simpler. Just swap these two items. And push and pop, that's like having a neat little stack on the corner of the bench where you can temporarily set an item down and then grab it right back when you need it. Now, it might seem really simple, but nothing else can happen without these movements. This is the essential prep work, the foundation, before any real crafting can even begin. Okay, so our materials are now on the workbench. They're organized and ready to go. Now it's time for our craftsperson to pick up the tools and actually start shaping them. And these are the power tools of the workshop. Opcodes like add, sub, mul, and div, well, they're for doing math. So when the CPU sees a command like add AXVX, it's not some complex formula. It's literally just being told, take the value you have in one spot on your workbench, called register AX, and add the value from another spot, register BX, and then store the final result right back into AX. It's simple, it's direct, and it's incredibly fast. But the CPU has more than just power tools. It's also got these amazing precision instruments for incredibly fine-tuned work. This is where logical opcodes come in, and they are so cool. Take a look at this. A command like this is like a neat little magic trick. It acts like a stencil or a mask. It lets you instantly scrape away the parts of the data you don't want, leaving behind only the exact bits that you need. This level of fine-tuned control is absolutely essential for all kinds of complex programming. But here's the thing. A computer isn't just a calculator, right? It doesn't just execute one instruction after another in a straight, boring line. The real magic, the secret sauce, is that it can make decisions. It has a blueprint to follow, the program, and it needs to be able to navigate that blueprint, to make choices, and to jump around when needed. And that really is the key question, isn't it? A program is rarely just a simple A to B to C list of tasks. It's full of if-then conditions. If the user clicks yes, do this. If they click no, do that instead. This ability to choose a path is what makes a computer so incredibly powerful. And this is how it works. It's actually pretty elegant. The CPU performs a test. Let's say it compares two numbers to see if they're the same. It then checks a special status flag, like the 0 flag. If the numbers were equal, their difference is 0, and that flag gets switched on. An opcode like JE, which means jump if equal, sees that flag is on and tells the processor to leap to a completely different part of the program's blueprint. If the flag's off, no big deal. It just moves on to the very next instruction in line. It's a simple yes or no choice that forms the basis of all computer logic. To make that even clearer, just think of it this way. A JMP opcode is an unconditional detour. It's like the blueprint saying, stop what you're doing and go to page 5. I don't care what. But JE, the conditional jump we just saw, that's the smart detour. It says, hey, check your measurement first. Only if it's correct, then you can turn to page 5. Opcodes also help keep the whole blueprint nice and organized. I mean, if our craftsperson needs to perform a common task over and over, like building a standard drawer, the main blueprint isn't going to list all 10 steps every single time. That would be crazy inefficient. Instead, it'll just say call build drawer. The processor then jumps to that little mini set of instructions, gets the job done, and then the RIT command for return sends it right back to where it left off in the main plan. It's all about working smarter, not harder. Now, every master craftsperson has a few really specialized tools in their kit, for those very specific jobs. And the CPU is no different. So the CPU has opcodes designed specifically for handling text, or what we call strings. Commands like MOVS and CMPS can move or compare entire sentences of data in a single shot. It also has input-output opcodes, things like in and out. These are basically the workshop's communication lines, allowing the CPU to talk to the outside world, to get input from your keyboard or send output to your screen. So we've seen that opcodes are the fundamental verbs, the action words of a CPU. They are the commands that tell the processor to move, to add, to compare, and to jump. But this leaves us with a final, really interesting thought. If the opcodes are the verbs, what makes up the rest of the language? What are the nouns and the grammar that pull this all together? And understanding that, well, that's where the journey into the heart of the machine truly begins.